Hi, my name is Stefany Medellin Gonzalez. I'm a graduated student at the University of Guanajuato, and I've been doing this work with my advisors, Alma Gonzalez and Luis Ureña. First, I want to thank the organizers of Cosmology from Home for giving me the opportunity to present my work. Today, I'm going to talk about the formation of a structure in the universe and a scalar field dark matter model. As we know, the most successful model to describe the universe is ΛCDM. But there are several proposals that provide an alternative that can be explored. In this work, we study the influence of the scalar field dark matter model on the formation of a structure in the universe using the mass-power spectrum and the halo mass function as observables. But why scalar field dark matter model? This model proposed that dark matter is a very light particle with a mass around 10 to the 21 eVs that behaves as a whole like a classical wave. This model has a characteristic feature that it's a cutoff at the linear mass-power spectrum that can be reflected in astrophysical observables. So, in particular, we are interested in the nonlinear regime of two cases. The free case, also known as fuzzy dark matter, is represented in the figure on the left side, where we see the linear mass-power spectrum for the model and ΛCDM as a comparison. And in the figure on the right side, the action-like potential case that were calling the extreme case. As we can see, in addition to its characteristic cutoff, we can see an increase in the amplitude of the spectrum before the cut. To do the analysis, first we implement the scalar field dark matter model into the code MG-Piccola to solve the evolution of the structure. This is an hybrid code that is specialized in modified gravity. With this implementation, we take advantage of the mathematical similarities that our solution has in comparison with the code. So, for this implementation, we take the non-relativistic equations of the scalar field dark matter model, which is a GPP system. In the equations 1 and 2, we have the Planck constant and c as the wave function. C, it's the speed of light. M, it's the boson mass. Phi, it's the Newtonian gravitational potential. Lambda, it's a self-interacting term. And G, it's the Newtonian gravitational constant. So, we take these two equations and use the model transformation, where the wave function is related to the density field, so and the velocity field. With this, we obtain a fluid-like system, and in the equations 3, 4, and 5 that we can see. In the equation corresponding to the Poisson equation on the right-hand side, we can see a combination of the linear and nonlinear functions of the matter density. And this can be seen as an effective gravitational potential. So, using the perturbation theory, we found the equations of the scalar field in terms of the growth factor. This equation is scale dependent, but we can recover the case of the cold dark matter using mu equal to 1. And to make the approximation to the nonlinear regime, we rely on the expressions that are found in the MG Piccola code paper. For the second order growth factor, we can recover the cold dark matter case if we make gamma 2e equal to 0. These equations are implemented in a really easy way to the code. Now I'm going to show you the results of the implementation. Here we have the free case, the action-like potential case, and for reference, the ΛCDM case. All the simulations have a box size of 15 MPSs and 1024 cube particles. That corresponds to a value of the shock noise equal to 3 to the minus 6. We call CIC to the one simulation that corresponds to a typical cold dark matter simulation with a cold initial condition. The FIC plus QP simulation corresponds to the free case with a fuzzy initial condition that is encoded in the parameter lambda equal to 0. In this simulation, the modified gravity function of the code are active to take into account the quantum potential. And finally, the EIC plus QP simulation corresponds to the extreme case with an action-like potential encoded in the parameter lambda equal to 8 to the 4, and with modified gravity functions active to take into account the quantum potential too. The mass of the boson for these simulations is 10 to the minus 23 EVs, even when this mass has been excluded from the observations. We use this parameter to enhance the effects of the quantum terms and as a proof of concept. The results of the simulations are these. First, I want to show you a projection of the density field and at redshift 2.5. Here we can see by eye that the scalar field has a significant influence on the structure formation in comparison with cold dark matter. As we can see in the fuzzy initial condition or free case, the density field shows a lack of a structure at small scales. On the other hand, we can see the case with the quantum potential active, and we can see that there is no much difference between the fuzzy initial condition and this case. On the other hand, we can see the extreme case that shows more structure in comparison with the cold initial condition simulation. So we can expect, we can expect the difference for these three cases in our analysis. And for this, we use the mass power spectrum. The results of this are this. Here we see the evolution of the power spectrum. For all cases, in gray, we put two lines of reference. The slanted line represents the scale of the shot noise, and the vertical line, the scale of confidence in our results. In the free case, the power suppression of the small scale vanishes and start to approach to that of cold dark matter at a small scale, redshift. And in the action-like potential case, we observe that the excess of power and the cutoff vanishes too. This behavior can be explained by the transfer of power from large to small scales. So, in all cases, the scalar field dark matter model starts to approach to cold dark matter case in the redshift, in small redshifts. These results are extensively discussed in the paper that we publish, and you can find in this archive direction. So the next step was the study of the halo mass function. A halo is an overdensity in the dark matter density field. To analyze this, we use the halo mass function, which encodes the comoving number density of dark matter halo and as a function of the halo mass. In particle simulations, like of models with an initial cutoff in their linear power spectrum, like the scalar field dark matter model, we found a proliferation of spurious structures. As we can see in this work, where show with open symbols the behavior of the increase of amplitude in the mass power spectrum for lower masses. In our case, we used the Rockstar code to make an auto catalog using a simulation of 512 cube particles, and we found the same behavior as previous works that shows an increase in amplitude in the halo mass function for low masses. To remove these spurious structures, we use techniques used in previous works, like the one that I showed you in the last slide. As a first approximation, we use a mass limit that is related to the characteristics of the simulations with the size of the box, the number of particles, and the maximum amplitude of the dimensionless linear power spectrum, and cut over all masses up to this limit mass. On the other hand, we study the sphericity of the proto-halos, which we identify as the first overdensities in the simulations at redshift 7. We put limits on the sphericity and the triaxiality of the proto-halos and remove those that have low sphericity. Here I show you some figures where we plot the sphericity as a function of mass and the triaxiality as a function of mass for different cases like lambda CDM, the fuzzy dark matter with a box size of 65, and the fuzzy dark matter with a box size of 15. So the result of the procedure is this. Here we can see the halo mass function for the CDM case in black and the fuzzy dark matter case with a box size of 15 MPCs in blue and 65 MPCs in gray. In the faint lines, we put as reference the semi-analytical halo mass function of the scalar field dark matter model and the lambda CDM model. This is the work I have been doing, and we are still working on other techniques for the remotion of spurious structures and other related projects. If you have any questions, my email is on the cover. Thank you for listening, and that's all. Thanks.